Okay, in this chapter, we want to just go through the small kind of short history of complex numbers. And eventually, the needs of complex numbers came from the, the needs of to having a solution for that kind of equations, right? So of course, in that equation, we know the answer should be plus minus 1. But we don't have any real numbers which is satisfying that its square becomes negative. But when you look at this, let's just use letter A. And A can be any real numbers, not only positive numbers. And still we want to have a solution for this. So if A is positive, yes, we have the answer. And usually that is x equals plus minus square root of A. But we don't have any real solution when A is negative. But let's just kind of assuming there is such number out there. Then the notation for that could be plus minus square root of that. We want to just apply same formula for this. So the only difference here is if A is negative, so for example is negative 3, then x squared equals negative 3 should have the solution like plus minus square root of negative 3. So let's just accept that, right? Okay, there are certain numbers like that out there. Then how can you write down that number? What is going to be the symbol for that, right? Through the whole course, we are interested about the symbols, right? From the beginning, how we define it. Then the typical formats, the forms of these numbers from that kind of equation is always like a square root of that number, right? So this is kind of typical forms of it, right? Square root of negative something. Then in algebra, we had that formula, square root of a times b is square root of a times square root of b. Of course, in that case, ab should be positive. But how about just extend this formula to this case? Then square root of negative something is same as square root of negative 1 times something. Of course, our assumption is that something part is positive, right? Then when you apply this rule here, then we can change that onto square root of negative 1 times square root of that something part. And that is positive, and we know what this one is. So the only unknown so far is this one. So if you accept that as one of our number, then we don't have any trouble to accept this one as another number, and that is same as that. And the meaning of that number is when you make it, we got negative, that's something number. Okay, so okay, let's just make this one as one of our number. Okay? And of course, we don't have any number like that in our real number system, so we call that as imaginary number. And this becomes imaginary units because all the other imaginary numbers, right, for the solution of such thing can be written by product of the real number with that. Okay? So we can put this one whenever we need it, but we are going to use this one a lot. So we just use like italic I is the symbol for square root of negative 1. And the I came from the initial of imaginary number. Okay? So once again, what is the property of I? If we make it square, it becomes negative 1. Now this is not the only one. If we make the square for negative I, then it's still negative 1. Right? Like square root of 2, make it square is 2, and negative square root of 2, make it square is also 2, right? So we have plus minus square root of 2. We have two numbers. When you make square of them, becomes 2, right? Same thing happens. Plus minus I is just two numbers. When you make it square of them, it becomes negative 1. Okay, so last thing, so negative I means negative square root of negative 1, right? So the following ones are just kind of short history about where this idea came from and who made what rules. And so please check these parts and the textbook, okay, all together, and what is the needs of this number. Okay? We want to get the solutions from certain equations like that. So let me skip this one. So Cardano introduced that complex numbers, so combination of real part and imaginary part. So that number can be written by a plus ib. Then for any real number, we already find out that there is a nice one-to-one correspondence between the points on this real line and the all real number set. Then how if we have this one as a new number system, then actually when b equals 0, that a plus ib becomes a real number, which means this one contains the entire real number with that condition only, right? So when b becomes 1, b becomes negative 2, we have that many elements, okay, every time like that. Of course, there is something more about that arguments, but anyway, so how can you write down that relation, and how about most nice model for that? Now how many choices for b? Another real numbers, right? We could just put any real numbers here, like the square root of 2 even, right? So a plus I square root of 2 is also possible. So we have that many choices for b. So the combination of these two possibilities, a can be any real number, and b is also can be any real number, and a can be written on this real line. Then if you just put b like that way, then these Cartesian coordinates, and when you look at any points on it, a comma b, this is really nice one-to-one correspondence between the points on this xy plane and the points collecting the set of these points. Okay? So we call that is complex numbers, and it's a collection of, let me write down this way, a plus ib, and ab's are all real numbers. Then this set and the points on this xy plane, there is nice one-to-one correspondence. And because of that, this complex number is good notation for the points on the xy plane. So suddenly we have another method to denote the points. So far, our method was ordered pairs, right? Like a, b, this point is written by a comma b. That's the only method. But now, from now on, instead of a comma b, we can just matching that one with a plus ib as a representative of a complex number. Okay. Then the question is, can you include some kind of relations on that complex number set? And how about operations like additive and multiplicative, everything? Yes, we can define it, and it's nicely done. So please check those steps. And that formula is actually later. Okay, you can in the second section. So let me just discuss about that. Now, we didn't cover that one in our course, but if you have a unit circle, and when we choose any point here, say x comma y, then is any way to get the actual values of x comma y for any arbitrary points on this unit circle? Yes, and the method is we just find out what is the angle between that line segment connecting the origin and that point and the positive direction of x-axis. So for example, if that angle is 30 degrees, then there is a right triangle. Okay. Then, because it's unit circle, this is the radius of it, so it must be 1. Then we already checked this one in the previous chapter, like if you have like that, then the ratio is 2, 1 square root 3, right? So it goes to 1, then this one is 1/2, and that is square root 3 over 2. So when you look at that case, it's 0, 0. Therefore, the coordinates of this point use that, which is square root 3 over 2. And this value is same as 1/2, so it's going to be 1/2. So that coordinates is square root 3 over 2, comma 1/2. So when you think this one in arbitrary theta, then when you look at this right triangle, the radius is just 1 always, the hypotenuse of this right triangle. And this must be, that is x, right? But x stands for that. So this portion is x, the length for x with the direction 2 is same as cosine theta. When you look at it, what is cosine theta? Is this length over 1, right? And that length is same as x, so which means is x, right? For the same reason, this height is same as this y, right? Y coordinates of that point. And sine theta is y over 1, which is y, right? So when we have any arbitrary angle theta, then that intersection points on the unit circle, the coordinates of it must be cosine theta, sine theta. And then one big result from that one is just choose anything, and for that theta, the coordinates is cosine theta, sine theta. Then when you look at this right triangle, we know this is cosine theta and that is sine theta, right? So the length is cosine theta and this one is sine theta. So by the Pythagorean theorem, cosine square plus sine square equals 1, right? So from the Pythagorean theorem and with this concept, we got the number 1 and the most powerful and basic identity in trigonometry. And this is not only true for the angle in the first quadrant. Theta could be anything, but still this cosine theta, sine theta is working. So from that point of view, in those xy plane, if we choose any point, and that is a plus ib, then you can imagine that point is on a circle. Like that, then we can find out the angle for that. And a plus ib means this is a, and that is b, right? So we know what the radius is, right? This radius, or the distance from that point to the origin is square root of a square plus b square, right? That is r. Then, when you think that circle with that unit circle beforehand, okay? So let's say it's a unit circle, and that one is r, right? Radius r, and that a plus ib is the given point. But when you imagine there is a line passing that to the origin, then we have same theta, right? Then this point must be cosine theta, sine theta, right? And that is 1 and this is r. So we are going to get similar triangle, right? This the small one and large one. The ratio is 1 to r. So this one was cosine theta. Then this one must be r times cosine theta, right? And that one must be r sine theta, which means those ABs is r sine theta and B is r, A is r cosine theta and B is r sine theta. Right? And that's how we got for any point on this complex plane can be written by r times cosine theta plus I sine theta. Where does it come from? Is a coordinate on a point on unit disk, right, or unit circle. Okay, so it's kind of really nice way to find the position, locate that point on xy plane. And there is something more, but we are going to cover this one in complex number course. Okay. And another thing is, and because of that, when you try to look at the roots or the solution of that complex number equations, then these are actually the vertices of regular polygon on unit disk. Okay? So it's like this. Let's try to find the solution for that. But in algebraic approach, we can have, then take the square root of it. Okay, so looking for what value makes that is 1, right? But it's plus minus 1. But right now, this plus minus 1 is not just real number as the real number point of view, no, but it's on xy plane or complex plane. 1 is here, negative 1 is here. So meaning is plus I times 0, right? So it's actually 1 comma 0, negative 1 comma 0, right? Exactly like that. Then how about z to the fourth equals 1? Then it's going to be z square equals 1, which means z square equals plus minus 1. So we have two things. First, z square equals 1. Then we already know that z must be plus minus 1 plus I0. Okay? The second case is z square equals negative 1. Then we know z must be plus minus I, right? Then that is 0 plus minus I times 1. So that 2 points must be 0, 1 and 0, negative 1. Where are they? It's here, 0, 1 and 0, negative 1. Right? So when you look at this, very strange thing happens. Just imagine we have a unit circle, and the solution for that is here. And solution for that is these 2 points and that 2 points. So can you guess what is the solution for that? Z cube equals what? Okay, there's a way you can solve it. Actually, you can calculate like this, and that like this, right? So z equals 1 or z squared plus z plus 1 equals 0, right? Then that, please try to find it, then place on the unit disk, then you can realize those 2 points are here. So z equals 1 means here, right? So actually, the solution for that is the vertices of regular trigon, regular triangle. And if it's 4, then it's the vertices of regular square, right? Regular foreground. So you can imagine if it's z to the fifth one, then you can just have nicely arrange these 5 points on the unit circle, and they are the vertices of regular pentagon. Okay, so you can have those rules. And in the homework, you're gonna kind of try to find those steps. Okay. Okay, so please just read this one. And okay, then how about the operations, right? How about the addition and multiplication? So for addition or subtraction is easy by the coordinate by coordinate, right? So x coordinates together, y coordinates together. But for multiplication, it's a little bit complicated, right? So, but that's what really should happen. So in this case, it's a little bit difficult to see that way. But when you look at that product, like a comma b is to a plus ib, right? And c comma d is c plus id. So if you treat them as general, regular product with addition together, then by this divisional ac plus I times AD plus I times BC plus I times IB times ID, right? So altogether, AC and these two terms have I as a common factor. So factor out I, then we have AD plus BC. And from here, it looks like when you multiply them, we have I squared BD, right? But what is I squared? Is negative 1, right? So we have negative BD. So this is just the real numbers, right? So when we arrange them like real parts and imaginary part, we have that. Then let's just convert that one to the order period style. Then AC minus BD, comma, AD plus BC. And that's where it comes from. Okay? So it's nicely defined to get to accept this type of algebra identities is working for the complex number system too. Okay. So that's it. So now, as you can see here, for any, for the complex number set, we give these two operations, addition and multiplication. Now, we have developed the number systems, right, in the previous several chapters, right? And in most cases, those numbers are kind of equivalence classes, right, for each given situation. The complex number set is not a set of equivalence class. Careful. It's just each one, single of them is its own kind of a number. Okay? So it's just ordered pairs. That's it. Set of ordered pairs. The rules are just given like that. Okay? So it's kind of a little bit different, but if you just think, yeah, each point is just equivalence class of its own one. It's not gathering all together and represented by a certain number or certain symbols, right? What you have done for integers or rational numbers, right? Not like that. You just read, yeah, each single point is its own just equivalence class, right? You can imagine that, right? But no needs for that. So you just think complex number set is just set up ordered pairs with those specific rules for addition and multiplication. And because of that, 1 okay, and I, each of them is the additive and is a one is a multiplicative identity. Okay? And of course, 0, 0 is the additive identity, of course. And even yi squared equals negative 1, not like I came from the solution for this, not like that, but I itself is written by 0, comma 1, right? Because I is 0 plus I times 1, right? Like that. So the product, if you follow that rule, then we will show that is same as negative 1. Then by accepting these complex number systems, if you have any polynomial with all these coefficient and constant terms are complex numbers, then this polynomial has exactly n solutions. We also have to repeat this, right? But like complex roots are possible. So now we have really that fundamental theorem of algebra, right? For any polynomial has n solutions, right? If you accept repetition. Okay? So it's the one. Okay, so yeah, let me stop here, and in the next video I'll show you some very interesting geometric representative of a solution for quadratic equation.